Welcome to the GaN Talk podcast, brought to you by EPC and hosted by Maurizio Di Paolo Emilio, Marcom Director at EPC. This show brings to life the stories behind GaN technologies and products. In each episode, you'll hear engineers, executives, and academics share insights on the challenges and opportunities shaping the GaN market. Here is your host, Maurizio Di Paolo Emilio.
Hello, everyone, and welcome to this another episode of GaN Talk podcast. Today, we will talk about GaN FETs for space, from qualification to space grade power. So, as you know, wide bandgap semiconductors are reshaping power electronics, and GaN, gallium nitride, is now moving into one of the most demanding frontiers of all, radiation-hardened and mission-critical systems. From satellites and deep space exploration to defense and high reliability aerospace platforms, engineers are looking beyond silicon to achieve higher efficiency, power density, and system level performance. So today, in this episode, we explore what it really takes to make GaN FETs radiation hard and QPL qualified with the CEO of EPC Space, Bel Lazar. Hi, Bel, welcome aboard. How is everything with you?
Hi, Maurizio. How are you doing? I'm doing great. Thanks for having me on. And first, I'd like to welcome you to EPC. I am so glad that you have joined us. You're going to make a tremendous change, and things will be much better under your leadership. So, welcome.
Thank you.
And
Thank you so much.
I'm excited to dive into how we're pushing GaN into the most extreme environments out there.
Good, very good. Thank you so much, Bel. Much appreciated. So, I have prepared a couple of topics and questions that I would like to share with you. So let's start talking about GaN in space. So from a device physics and system architecture perspective, so what makes GaN particularly attractive for radiation-hardened power electronics compared to silicon MOSFET, and even silicon carbide?
Sure. I mean, GaN's wide band gap, which is about 3.4 EV versus 1.1 for silicon and 3.2 for silicon carbide, lets us achieve much lower on resistance and higher breakdown voltages in a small, tiny die, which translates to dramatically higher efficiency, power density, and switching speeds. For space systems where radiation matters, GaN is superior when designed for radiation. As a matter of fact, even when it's not designed for radiation, in general, it's superior. But let's say it's designed for radiation, it gives us a much better, more superior product. In addition, GaN devices are often 10 to 40 times smaller and more efficient than rad-hard silicon MOSFET, let's say. Compared to silicon carbide, GaN shines in the 40 to 300 volt range, which is typical for satellite power distribution. As faster switching means smaller passives, less heat, and overall lighter systems. And we've seen designs where GaN cuts converter size by at least half while boosting efficiency.
Great. So when GaN FETs are exposed to radiation, so what are the dominant degradation mechanism engineers should be worried, should be most concerned about?
So EPC's GaN devices are total ionizing dose, or TID immune. They just don't fail. There's no oxide layer, just don't fail. TID, so we can take TID out of the equation. Now, under single event effects, the degradation mechanism is typically in higher leakages. Our GaNs don't have a rupture or burnout failure mechanism like silicon. But we do have, if it's not designed properly, we do have a degradation in terms of higher leakages and not meeting the datasheet spec. So to address these issues, we have designed rad-hard products that meet the data sheets with an LET of 84 MeV, which is with a very high fluence rate, by the way, of 1 e⁷, which is the gold standard in terms of requirement for a single event.
So the term QPL is used frequently, but sometimes not explained in depth. So what are the main technical steps and approval processes required to qualify a GaN FET for a QPL, so a qualified product list? And talking in terms of standard, which military or space standards typically control the qualification of rad-hard GaN power devices, and how these flows would differ from traditional silicon-based QPL parts.
Sure, no problem. The QPL term, it's an old term. It means it's listed on, there's an agency called DLA, or Defense Logistics Agency, which is part of DoD. It means qualified product list, and it's the gold standard for high reliability military space. I mean, the process starts with the facility and foundry certification, then rigorous product qualification. And there are military standards, for example, like MIL-PERF 19500 and the MIL Standard 750, which have the test methods, and these are for discrete devices. For ICs, there's a similar MIL-PERF, they're called MIL-PERF 38535, and there's MIL Standard 883. These documents have extensive electrical and mechanical reliability testing to ensure products operate for tens of years in harsh environments such as space. EPC and EPC Space were the first to qualify a QPL GaN product, rad-hard GaN product, and so we're very, very proud of this. And then we have qualified products from 40 volt to 300 volts, and now we are offering 18 QPL products, which is a major milestone for EPC Space, and for the industry, as a matter of fact, to be able to provide a rad-hard GaN on a QPL list.
So talking about the different GaN architecture, so from a radiation and qualification standpoint, how do enhancement mode, depletion mode, cascade GaN architecture compare? So which is best suited for space-grade applications?
Sure, it's a good question. Enhancement mode GaN, like our eGaN devices, are normally off. So gate drive is straightforward with positive voltage. On the other hand, depletion mode is naturally on, requiring a negative bias or cascade setup. Now, cascade adds a silicon MOSFET in series, which can introduce a mismatch on the radiation or thermal stress. So from a rad-hard view, enhancement mode wins. Just fewer components, which means lower failure risk, easier qualification, and we have proven a superior single event effects, or SEE, and TID immunity. It's the architecture best suited for space. It's reliable, efficient, without any extras.
So talking about packaging, so how critical is packaging in radiation hardened GaN devices? So what failure mechanism, failure modes are driven more by the packaging than by the semiconductor die itself?
Yeah, I mean, for our devices, and packaging is not critical in terms of when it comes to radiation effects. Because you can take our die actually without a package can survive TID or single event when it's designed for radiation hardness. However, packages are critical for ease of use and thermal management for the user. So we put these parts in packages to allow the user to for ease of use. In addition, we use many of these specifications require you to have what's called hermetically sealed packages, and we use hermetic ALN packages. Since hermeticity is a requirement in many space programs and other harsh environments.
So talking about product solutions, so EPC Space recently has introduced evaluation board, a three-phase motor drive evaluation board designed around the EPC 7C021, so the rad-hard GaN power stage. So can you explain, can you say more about this platform and example of applications?
Sure. I mean, this demo board or evaluation board is a full-featured three-phase motor drive. It uses our rad-hard GaN power stage IC and EPC 7011. This is the world's first rad-hard power stage IC, and we're proud to have introduced it to the market about 3 years ago. And it shows how GaN enables compact, high-efficiency motor control for up to 400 watts in a small footprint. It's this evaluation board functions as a standalone three-phase motor driver, but it could also support connections with EPC's EPC 9147A controller card for advanced closed-loop controls. I mean, you mentioned about what are the key applications. Key application includes satellite reaction wheels, electric propulsion actuators, pumps, robotics, etc., and deep space missions, where you need like lightweight, radiation resistance, power without sacrificing performance.
So EPC Space also recently introduced the EPC 7030 MSH, so 300 volt radiation hardened GaN FET with the goal to work at higher voltage satellite power systems. So can you explain why 300 volt rad-hard GaN devices is important for for modern satellite power architectures?
Sure. I mean, this is a fantastic device. I mean, it's a 300 volt, 50 amp. I mean, low RDS(on). It's just it has the wow factor. Yeah. More and more satellites are pushing the limit in terms of bus voltages, and they're going to higher DC bus voltages. This is to minimize distribution losses and support higher power systems requirement like electric propulsion on large arrays. A reliable 300 device like this one lets designers build efficient front-end converters without paralleling, and also cuts size, weight, and complexity, while of course maintaining the rad-hardness and its performance. Moreover, in addition, the 300 volt devices would give designers plenty of room for derating if they choose to do so. We know our space architect engineers love to do derating, and so a 300 volt would give them plenty of opportunities to do so.
So talking about other applications, so what are the other main aerospace and defense applications where rad-hard QPL GaN FETs are already being used today?
So, currently 100% of our space products are used in space missions. Satellites, launch vehicles, scientific spacecrafts, etc. And if you have a QPL part, then engineers and buyers do not have to worry about. This is the reason we're having QPL, but the main application are space. But also, don't forget the QPL would allow engineers and buyers to not worry about quality and reliability, as these QPL products are monitored and managed by DLA, and buyers don't have to generate what's called a technical procurement document like an SCD, and hence purchasing a rad-hard GaN much easier and less bureaucratic. But most of our sales today, actually 100% of our sales, they are for space, and we're trying to venture outside this by offering what we call rad tolerant, but right now it's 100% of our sales are in space.
So thank you, Bel. So we have seen different topics. I like to highlight, to focus on your evaluation board. That is a nice board, standalone three-phase motor drive for different applications, as you mentioned, and your latest device, 300 volt radiation hardened GaN FET. So in conclusion, a look at the future. What's new on the roadmap from EPC space? How do you see the market evolving in the next years? Expectation for 2026?
So we're looking at two things. We'll look at, let's say, on a discrete side, we actually went down in voltages to cover this growing market of point of load. We have just recently developed 10 volt, 25 volt, and 40 volt product rad-hard GaN FETs that will be announced sometime in April-May timeframe. And this is fantastic. It has not been done before in terms of GaN rad-hard. So it's our world's first again, and we're proud of that. In addition to the fact that we've covered now a good range of voltages on the discrete, a range of voltages and currents, we have also now expanding our rad-hard IC portfolio. Recall that we have the rad-hard IC power stage, and now we're going to be launching this year a rad-hard low-side driver, and then we'll be launching more rad-hard power stages and rad-hard FET and ICs on one chip. So on the non-discrete side, the idea is integration of discrete devices into ICs, and that's going to be the future is rad-hard ICs.
Great future with EPC space. Thank you, Bel. So thanks a lot. It has been an honor having you. So thank you for joining us here on the GaN Talk podcast. I wish you a great day, and I look forward to talking again soon. Thank you.
Thank you, Maurizio. The honor is mine. It was a pleasure talking to you.